So, today we will be looking at cohesive soils and their behavior under different moisture content. So, if you look at this picture, you can see the increasing moisture content transform the soil from solid state to a liquid state. As you can see, if you look at like coastal areas, many of this the very soft clay becomes almost like a liquid. When you step in, it will just go down. So, you can see the three states: solid, semi solid. The demarcation is slightly difficult to determine, but at least from semi solid to plastic, plastics to liquid, there are two immediate the demarcation we can find out. One is liquid limit, beyond which the soil will actually behave almost like a liquid, and on the other side it might become plastic, that is deformation will take place, but cannot return back. So, basically the plastic limit is the liquid state, almost like a liquid state, but not too much of a liquid or a fluid added to the soil. So, it will become plastic state, and on the other side, if you keep reducing the moisture content, it might become either semi solid or almost solid state, which will retain the shape irrespective of the small amount of moisture what you have. So, this will tell you when you apply loading to a cohesive soil with different percentages of moisture content, you could see basically how it is going to deform. So, that is why we need to determine this percentage of natural moisture content in a soil. So, how do we determine and what is these limits? Of course, finding out the moisture content in a soil is very easy. You can actually weigh them in a dry state and the natural state, and the difference will give you the natural moisture content, but the limits of demarcation, whether it is a semi solid or plastic state or liquid state, just an empirical method, of course devised by past researchers. Several methods are there. We will just discuss one of the method which will give an idea. So, basically we want to do plastic limit and liquid limit determination based on two of the methods. One is Casagrande method, the other one is Falcone method. The reason why we need to find out this and why we need to know this, though they are not directly giving us the strength parameters, one of the important idea was the previous literature, the past data, people have tried to relate these two limits to the possible determination of classification as well to some of the design parameters. So, if you know for your soil this particular limit, then you can go into the literature, find out what kind of strength this will have, what kind of deformation characteristics it might have. So, all these ideas are related to this limits. So, that is why we need to find out. One important thing is the differential fluid limit between the plastic to liquid state. So, basically it is called the plasticity index, that gives a very important classification of soil, how much, whether it is behaving as a plastic side or to a semi solid. So, that is why we need to find out the plasticity index. The larger it will become almost like a fluid. So, that is where we want to find out these two limits. So, we will just quickly look at what it means. So, liquid limit is the moisture content beyond which the soil starts behaving as a fluid, it is just flowing. If you just pour it or drop it onto the ground, it will become flat almost. You can find out using crank and cup method. I will show you the photograph just a little later. So, if you look at the photograph of the crank and cup, is a device I think you might have seen in your laboratory in soil mechanics or geotechnical lab. You have a crank and you have a counter which will actually be used to count the number of times you lift and fall down of this cup. In this cup you will fill up the soil something like this and make a groove. You see that small groove of 12.7 millimeters. So, several times you rotate it, and automatically if the soil is having flow characteristics, it will just try to join at the center. So, the number of times that you rotate the crank will tell you whether it is close to fluid or close to solid. So, basically that is one of the machine which I think from olden days people used to use, little bit troublesome, but then it is quite good. The other one is the Falcone apparatus. You just make a sample of your soil into the cup and then allow this cone to fall down. You can see if it is a very good soil, strong, the cone will not penetrate too much, but if it is like a fluid, it will penetrate larger depth. So, that you can understand easily. The Falcone is a direct indication of how soft or how fluidized the soil is. So, this method also can be used. So, the criteria for crank and cup method is basically the moisture content corresponding to 25 blows. That's the kind of idea they were devising earlier on. So, we will still use that, and the formula to calculate the liquid limit, if you do not want to plot in the log paper, semi-log paper, you can use this formula. The number of blows is n, and basically the Wn is the natural moisture content for that soil. Fall cone test, the cone is having a apex angle of 30 degrees and the weight is 0.78 Newton. So, that means it is a very small cone, and the moisture content that corresponds to 20 mm penetration. So, what you will normally do is you take the soil, change the moisture content several times, that means you will add and then put it into the same the cup, allow the cone to penetrate, and you do the test several times, that means with different moisture content. Plot on a graph. In fact, I have given you the procedure here. Basically, is just repeat the test few times with different moisture content. So, you will have different fall cone penetration and put it in a graph. Then you just look at the moisture content corresponding to 20 mm of penetration will be your liquid limit. Similarly, when you come down to Casagrande method, you will also repeat the test few times by changing the moisture content, that means you will add water, and then you plot in a semi-log graph and you find out what is the moisture content corresponding to 25 number of blows, and basically that will be your liquid limit. So, finding out a liquid limit is very simple idea. You take the original soil sample, do the test and take the sample, reduce the moisture content or increase the moisture content on either side, and then do the test also. Then you plot it and you will find 25 blows corresponding to moisture content will be your liquid limit, or if it is a fall cone 20 mm penetration corresponding moisture content will be your. So, these are just a very simple ideas to find out how much moisture content corresponding to either 25 blows or to 20 millimeter of penetration. So, these procedures are actually given in this ASTM D4318. Of course, you will also find in some of the IS codes. I could not pick up the Indian standards, but I think it will be there somewhere. But most of the offshore applications we use ASTM for marine situations, whereas IS codes does not talk about. Similarly, for the fall cone procedure, you have BS code 1377, which is complete procedure, and the fall cone weight and basically the apex angle, number of times to repeat, quite a number of procedures are given, you should strictly follow that. So, liquid limit is very straightforward. Similarly, we can find out the shrinkage limit. I think we saw on the left side of the various states of the soil, as much you keep reducing the water content beyond certain water content or moisture content, what will happen is the soil volume does not change. So, you can see here from a liquid state to a semi solid state and to a solid state, certain moisture content still will be there, but the volume will not reduce, that is called a, beyond which the soil state will not change much, that is called a shrinkage limit. The procedure to find out is given in another ASTM code, which is basically similar to the liquid limit test. Plastic limit determination, historically people have been using this idea of rolling on the finger on the palm foot. So, plastic limit is the moisture content which soil crumbles when rolled to a particular diameter of 3.2 mm as a thread. You just keep doing it, beyond which, so if it is a liquid state you can't roll, if it is too much of a solid state you will just roll, it will just break, it does not have sufficient water content or moisture content. So, you just have to repeat this. So, until you can see on the right hand side it crumbled. So, this is a little bit troublesome method because it is not very easy and it is time consuming, but the procedure is acceptable as the ASTM gives you this. Also, I think you will find in other codes. One of the alternate method was, this fall cone method was also devised to find out the plastic limit, exactly same procedure as liquid limit, only thing is the weight is slightly bigger. You see here, instead of 0.78, I think that is what we were having, you just increase the weight of the fall cone to 2.35 Newton, and basically you will repeat the same procedure few times and you can see here there are two graphs. One is the black color one, which is cone weight is 0.78 Newton. On the right hand side you see the cone weight is 2.35 Newton, and basically this 20 mm gives you the liquid limit, and the same 20 mm in the other graph gives you the plastic limit. This seems to be a very simple procedure compared to the roll and thread method is basically a little bit difficult, but of course, if you are experienced enough, is not a big deal to do it, basically you can get it done. So, why do we needed all these parameters? We started yesterday with all this grain size distribution, percentage passing through 10%, 20%, 50%, 60%. Using D10, D60 and D30 we were trying to find out uniformity coefficient, coefficient of gradation. So, for coarse grained soils we have few properties which we were able to determine very easily. Similarly, for the cohesive soils or fine grained soils we are able to find out liquid limit, plastic limit and plasticity index. With this we can actually find out whether the soil is going to behave in which as a predominant way. In natural state you may have sand, clay and mixture. So, if it is predominantly sand, you will try to jump to some particular parameter of interest, whether we want shear strength, we want something other parameters. How do we determine? So, basically once you get this information, you can decide what type of test you want to do, whether I want to do a test in situ because the soil is too much of coarse grain. Even if I try to take sample from the site, it is going to be disturbed. So, it is going to be remolded. So, when I do it the test in the laboratory, I am not predicting the right strength because it is already reorganized. As you know very well, when the soil particles are repacked, strength will be different. Then the foundation soil in the natural state is going to offer a different strength than what the strength we are arriving at the laboratory. That is why these are some of the very initial tests. Quickly you do it, then you can get some kind of decision made. Of course, experienced people will be able to make even at the look, even before you do this, you will be able to decide I need to do a field test, I cannot take this sample because the sample is going to be getting disturbed. So, that is the idea behind getting these parameters, the preliminary or primary parameters. I will only look at the soil classification by unified classification system and the plasticity chart. Though if you look at the literature, you go to textbooks, you will find variety of classification ideas, but almost similar. What you see here is almost very close to every one of them. Even if you look at IS course, they have followed unified system. So, it is not a big change. So, these are some of the parameters you will see. Some of the tables which I have taken from the unified classification system will be using these parameters to decide whether it is a sand or clay or part of them. How do we classify is basically a simple idea. Notations, because it is repeated writing, is not very easy to remember. So, if you just remember these letters, it is easy to go and coin the name of the soil. So, you can see here G for gravel, sand, M for silt little bit because it is repeated, C for clay, organic soil, peat. On the right hand side the secondary basically grading, the first two of them is well graded, poorly graded. So, W and P, which is very easy, which is what we saw in our several graphs in the sieve analysis, is well graded throughout the spectrum of particles. You have the percentage passing through. Poorly graded, some of them are missing or gap graded. And then with respect to how much is fines content, basically non plastic or plastic, but of course with moisture content, and plasticity, high plasticity or low plasticity. You can see here the liquid limit less than 50% or greater than 50% gives an idea whether it is going to be highly plastic or not. So, these are some of the parameters which will be added to the primary classification, which is sand, clay and silt. Of course, the gravel very rarely you get into in the natural state of soil, very rarely, because you will find only very small fraction. So, typical example will be, for example, you see here well graded sand, poorly graded sand, organic clay with plasticity low or high, similarly silt with fines, silt with low plasticity. So, you can just, so this is what the description, if you actually have sufficient experience of doing field studies. You do not even need to actually know all these parameters. Straight away somebody can write this is definitely a kind of soil poorly graded, because I can see from there. Sometimes it might go wrong if you are not able to do it properly. So, that is the idea behind. So, if you look at this table, how do we classify? There is a requirement table. You can see here coarse grained soil, fine grained soil. I will just take a 1 minute to basically explain here how do we determine how much percentage. In order to go with the coarse grained soil, the coarse grains must be higher than 50%. For example, you take a natural state of soil, pass through your sieve analysis. For a demarcation of to be in a coarse grained soil, we needed more than 50% of coarse fraction retained on 2 mm sieve. So, you can see this is a, it is not 100% to be required. So, remaining can be any fraction below that particular size. So, that is what they have followed. In addition, you also have several other parameters, like you see here the uniformity coefficient to be in this order. So, you can put well graded gravel, you know. So, basically that is the idea behind. So, these are some of the parameters set. So, when you are doing a soil investigation for your site, you will take this table and just meticulously go through, but beforehand you will have to have these parameters, do all this sieve analysis and consistency experiments, bring the parameters to this table and try to, you do not have to remember all these numbers, because it is anyway available everywhere. So, but very important thing is, to be a coarse grained soil, to be classified in this particular group, you need to have minimum 50% or higher coarse grained particle sizing. Similarly, you see here fine grained soil 50% or more, if it passes through this particular sieve size, then 63 micrometer, then you will be classifying under fine grained soil, because predominantly fines, predominantly coarse grains. So, that is the most important one. You need to remember what is the percentage is higher than 50%, whereas all these parameters you see here, one is uniformity coefficient, you have plasticity index, and then coefficient of gradation. All these will be used to devise the sub classification of the soils among the coarse grain or in the fine grain. And some cases, whenever you actually have a plasticity index, you may not be able to directly classify, you may use or help from this particular chart, which is called a plasticity chart, which is giving relationship between the plasticity index on the one side and the liquid limit percentage on the other side. The demarcation is given and the notations are given there. So, you will classify the fine grained soil using this plasticity chart. The idea behind classification I have already explained. The reason why we need to classify, I think most of you should remember, the classification does not directly give any strength parameter. The reason we need to know what type of, where it adhere to, is to use the literature and the past reports and studies, so that you can extract some of the design parameters without doing any further field testing, or even if you do field testing or laboratory testing to your soil, you can always compare with what others have got, because the uncertainty involved in the soil sampling, bringing to the laboratory, carrying out the test is very high. So, if you do it yourself, plus based on the classification you go to literature and compare where do you stand, whether something reasonable or something unreasonable. So, always you will be doing that comparison. So, that is why this classification helps a lot, because you can refer to the past literature. So, basic idea is, this table is a criteria table by which you will go by one, and I have elaborated in the next 3 slides, just slightly taken into details, again coarse grained and fine grained, with sufficient information on percentages of fines, grading and plasticity. Wherever the plasticity is coming in, you have to go and use the plasticity chart to get the sub classification. So, there will be 3 pages, I do not think we need to repeat that, you can just follow through as you want to classify. So, if you are given some of the parameters, for example, percentage fines, percentage coarse grained particles, plasticity index, or basically Cu or Cd, Cu or Cc, you should be able to enter into any one of this table and try and classify yourself. Now, what next we want to do is look at the soil mass as three phase basically solids, and you may or may not have water, and you have voids with air. So, basically we want to see some of these relationship between. So, if you take a soil sample from in natural state, you will have solid particles, you might have voids or you might have full of water, depending on whether it is fully saturated soil or partly saturated soil. So, as we mentioned yesterday, most of our subsoil conditions in offshore, you will have fully saturated condition. So, basic idea is, so this relationship will help us in relating several parameters of interest, especially the bulk density. I think that is what we are looking at. Density plays a major role. Yesterday we were looking at. The second thing is, the amount of water, amount of voids, also going to give us an understanding of how the deformation of the soil is going to happen, and that is what we need to know. So, you take a soil sample, bring to the laboratory and do the testing to weigh the weight of solid particles alone, total weight, moisture content, and then the state of the voids inside the soil mass. So, this basically you see this diagram, this is VV is volume of voids basically together with the air and water. So, that is where the water is contained. The total volume is noted as V, and volume of solids, I think this must be VA, is a little trouble there. So, VA, VS and V, these are three, and VW is basically the volume of water. You can express this in terms of weight instead of volume. You also can use that diagram, either way it is going to be same. Some of the simplest thing is the saturation ratio. If it is 100% saturated, the volume of voids is fully filled with the water, basically. So, VW by VV, both of them are equal, that means is full, and partly means volume of water is going to be less than volume of voids somewhere. So, it can vary from 0 to 1. So, this ratio gives you saturated soil, partly saturated soil or dry soil, So, basically, and the next thing what we want to look at is the voids ratio, which is basically the volume of voids to volume of solids, honeycomb structure, basically. And then the porosity is denoted as a, I think you should be little bit careful about this N, because N is also used elsewhere in some other places, but of course, you should remember according to the notation wherever it is used. Here we are just using N as volume of voids to total volume will be the porosity. So, you can see the ratio of voids to total volume, here voids to solids. So, you get slightly different. You can also combine these two to get one from other. It is basically the relationship between, you can substitute into. So, the voids ratio can be calculated once you know the porosity, or you can calculate the porosity if you know the voids ratio, which will be very, very useful. So, what do we gain from here? If the voids ratio is larger, it is no good, isn't it? That is exactly loose soil. If the voids ratio is smaller, is better, that means its solid particles are more. So, that is basically an idea to get the deformation characteristics. Later on you will see that, and more the voids, more amount of water will get filled. If it is a saturated soil, that means soil will almost like a floating, and it may behave very like a fluid flow around when you apply the loading. So, that is the idea behind. The next parameter we are looking at is the bulk density, total mass divided by total volume, which is very easy to find. You just get the mass. The next one you can also express that in terms of specific gravity. So, total mass of solids alone divided by volume of solids into density of water. You can express in several ways, like for example, saturated soil is full of water. So, basically to get an idea of the bulk density. The most interesting or the important one for us for foundation calculation is the weight density, not the mass density or the unit weight, is the weight by volume, which is very easy also to get. Bring the soil sample and weigh it in a natural state, and find out the volume, and basically can express in terms of mass times gravitational acceleration also. If you have the mass, or if you have the weight, you can calculate the mass by dividing by 9.81. Also you can write in other forms by substitution of specific gravity, which I think you most of the time will be very useful. From one you can find out the others, and for us the most important one is at the last, the saturated state of soil is always going to be there in observed conditions. So, if you want to find out the effective unit weight, which is basically minus the buoyancy of the particles displaced by. So, basically you deduct the density of weight density of water, which will be the net, which will be going downwards. I have just summarized from various places a table containing which parameters can be calculated if you have some of the parameters among these 6 or 7 parameters what we have got, which will be very useful when you do not have something, you can calculate the others. So, just a list of equations. Just to give you an idea what kind of numbers we are looking at. For example, if you look at a loose sand, void ratio is as much as 0.8, and if you have a stiff clay, soft clay, you can see the parameters also nearly 1.4. Moisture content, when you look for something like this is very useful, because when you do not have data, you will always, when you have a description, loose sand, I want to find out what is the property. So, you search for several places, this type of collected information will be very useful. And in terms of weight also, you can see almost every one of them is less than 20. Now, if you look at the dense sand, it goes very close to 18 kilonewton per meter cube, very close to concrete. Concrete is around 20, 22, 24. So, you could see the dense sand versus loose sand, the major difference in density. Similarly, you look at the stiff clay versus soft clay is almost similar, 14, 13, 14 to stiff clay goes almost close to. So, stiff clay means void ratio will be slightly less, for sure well packed, particles are closer, and that is why you have the strength wise better, density wise better. So, all this is an indication of type of characteristics. So, either from here you try to assign properties, or from the properties you can come back and say this is this type of soil. The next one for basically for coarse grained soil is the relative density, very commonly used in the foundation design. You take a natural state of soil, you find out what is the Voigt's ratio and note down, and try to rearrange the particles to a loosest state or to a densest state, and that will give you an idea of the maximum Voigt's ratio possible. For example, you want to take the particles to the loosest state, it has to coexist as a soil mass. You do not want to take the particles separately, that will not be a soil, is not it. The loosest state means still it will be a particular state of soil which has got largest voids. The densest state is try to pack by means of disturbing it, that means you will either vibrate or reorganize. So, that will be the minimum Voigt's ratio. So, you can see here in relation to the maximum and the minimum Voigt's ratio, or the state of the soil, we try to find out the relative density in terms of percentage close to loose state or percentage close to dense state, that is called the relative density. How dense in relation to the densest state, or how close is close to the loosest state is called the relative density. This is very much very useful, especially in made up soils, some places like reclamations, or in fact, when you are making roads, we will use this terminology, because we want to compact it, and we want to compact as much as possible to a densest state, and that we need to specify, say relative density of 100% means it is a solid, there is no voids. So, you have to take one particle by one particle and organize to get the such a densest state, which is practically not feasible. That is why relative density of 70% is very good. 80% may be very good, but difficult to achieve. Whatever packing you try to do, you will not be able to do it. So, that is exactly the idea behind, you will not reach 100% relative density unless if you are able to get all sizes of particles within the soil mass. When you actually vibrate, the smallest particle go into the voids of the biggest particle, almost you will get 90%, 99%. So, that is the idea behind this relative density, predominantly used for coarse grained soils, especially sandy material, where you are trying to do compaction, densification, reclamation projects, roads, and in some cases even in foundations we actually dig out the ground. If the soil is no good, bring in a foreign soil and compact. So, your immediate layer, wherever you find the loose soil, soil replacement projects, basically replace it with the good soil, and then you start constructing your foundation, mostly on open excavated foundations, not on pile foundations, because you definitely cannot dig to that depth. So, this relative density is a interesting characteristics, which you will find it later will be related to several test strength parameters. In this case, the state of the soil is described and the relative density is given here. So, you see this table, loose 0 to 15%, that means lots of voids, loose, very loose, medium and dense and very dense. So, you can use this, and later you relate this with density. People have done studies in various locations. Loose means density is say 10 to 11, very dense 18 to 20, and with that two informations you can also relate that to some of the strength parameters like angle of repose. Yesterday we were seeing loose soil goes flat, so angle will be less than 20 degrees. Dense sand can go as much as to 30 to 40 degrees, 45 degrees. So, you can get that table inserted, will be very useful. As soon as you get your density of or the state of density, then you can find out the strength parameters. So, that relative density is in relation to the densest state of the soil or to the loosest state of the soil. Some of the parameters you can substitute with respect to White's ratio or porosity and relate them, so that once you have the parameters you can find out the relative density, which is of some use, but not very much important. So, I think with that we will try to summarize what we have understood so far is basically from soil particles of shapes and size and formation to coarse grained and fine grained properties. We were just picking up few of them. I ignored several of them which are not related to foundation design, and basically I identified only some primary parameters like fines, percentages passing through, which will describe the particle sizing, sieve analysis, coefficient of gradation and coefficient of uniformity for coarse grained material, and we went on to plasticity or so called plasticity index from liquid limit and plastic limit, and the way to determine. So, one of the method was crank and cup method, the other one is fall cone method. For plasticity or plastic limit, we have either the fall cone method or basically the second method for plastic limit is a thread, and then plasticity index. Using these 6 parameters, we were able to go into criteria to classify, unified classification system, coarse grained, fine grained. So, this gives you an idea soil is that much. What we have not actually gone through is how do we do it and where do we do it, is basically is called soil investigation. So, every time when you plan a construction of a structure either on land or on offshore, the first thing is you carry out subsurface investigation, sometimes we call it soil investigation, geotechnical investigation, trying to find out the strength of the soil. As much you have spent enough time in designing the structure with respect to strength and responses, you also have to investigate to the soil. So, we need to basically spend some time so that you can decide the structure type. I think in the design course itself we were looking at the soil type can change completely the configuration of the structure, whether it is onshore or offshore does not matter, because ultimately the loads have to go to subsurface. So, soil investigation is all about trying to determine the characteristic of soil, so that it can be used for load transfer from superstructure to substructure, substructure to soil. So, the whole soil investigation it requires considerable effort, in fact reasonable effort in planning. You need to determine what type of equipment is required. If it is a sandy soil, some type of equipment for picking up the soil. If it is a clay type of soil, some other type of equipment. If it is a rock, definitely both of them cannot use. You need a core drilling, because it is very hard, and number of samples is very tricky. The more is better always, but then the more also very expensive and time consuming. So, we need to determine how many is good to actually profile the soil at the site, how many in one location and how many at the site. For example, if you have a site of 1 kilometer by 1 kilometer, 1000 meters by 1000 meter plant, onshore plant, and you have structures spread all over so many places. So, how many of them you need to do? There is no rule book. This is one of the biggest problem. It is left to the engineer's decision, because engineer only the best person to assess how many is required for each structure, how many is required for profiling the whole site, so that anywhere you can construct. The best will be for an engineer to make a decision is every structure will have one at least, that will give an idea. But within the structure, if the foundation is so large, for example, you take one building in the site, 1 kilometer site, but one building is 50 meters by 20 meter, whether I will do one borehole at the center of the building, or I will do 4 of them at the corner, or I will do 4 of them one side, 4 of them other side, 2 of them another side, nobody is going to tell us. So, which we need to make assessment based on the variability of the soil at the site. If the soil is nicely uniform, you do one here, you do 1 kilometer away, you will also get the same type of properties, same type of layering, then there is absolutely no reason to go and spend too much of time. Probably what we do not know is within the diagonal at the center, whether it is going to be same soil or not, that nobody can say. So, unless you have more than 2 or 3 and try to profile, if the profile seems to be good, then you may actually take a decision not to carry out too many, but if the soil varies, then you really have to spend a lot of time. So, this planning is a tricky exercise, especially large plants, large construction sites, but for offshore projects not a very big problem, at least for platform projects, because platforms are not that much long, larger spread. It is going to be smaller footprint on the seabed. So, normally we plan one at platform, which itself is sufficient. If you have doubt, probably you can do a verification by doing one more in another corner, but typically for offshore projects is one at each structure location is well represented. But for pipeline projects is a big challenge. I think you might have heard of these subsea pipelines, when you have a pipeline coming from land to offshore platforms, you have several thousand kilometers. Now, will you do one or will you do thousands is the biggest question, because the pipeline is going to sit on seabed, but vulnerability of these pipelines failure due to soil is very less, because the loading is quite small. So, it is going to be transferring to the surface soil. So, you do not need to go deeper foundation holes or deeper geotechnical investigation, maybe a shallow is good enough, but as much shallow the number of them will be larger. If you have 1000 kilometer pipeline, imagine how many of them you have to do, even if you do 1 per kilometer, is not it, you have to do 1000 boreholes. So, there also you have to spend a kind of good planning to determine how many of them is required in a stretch. So, you will need to analyze the variability. In many occasions we do actually a borehole at wider spacing first, look at the variability, then determine intermediate boreholes. So, this kind of planning is always so requirement of equipment and boring has to be determined based on geological formation types. If you look at the history, this particular area is belonging to this particular type of geological formation. So, based on which you will be able to say predominantly clay on first layer, predominantly sand on second layer, historical information. based on which you will go and provide for type of equipment. Borehole location, depth, number, spacing, I think is a very complex scenario for onshore projects, whereas for offshore and pipeline projects is very much well determined. And you have choice of doing test in the site itself, which is called field test, or you bring the soil in an undisturbed state and do a laboratory test, which is commonly used, and then you can determine the strength parameters in addition to what we discussed so far, the grain size distribution and the consistency limits and additional density parameters plus the strength parameters, all of them can be done in the laboratory. Then use that to profile the soil to a particular layering, how the change is happening. Then from this you can find out what is the design soil parameters, advise to the engineers to use that for foundation design. So, the whole process is very much essential, without which you can't really design the foundation. We will look into details of each one of them.